To get us started, I want you to think about this simple question. Why do lemons placed in a glass tumbler full of water suddenly appear so much bigger? Or why does a pencil look like it's literally broken when you dip it into a glass? These aren't just random tricks of the eye. They're everyday mysteries just waiting to be solved by the beautiful underlying physical laws of our universe.
So here is our roadmap for today. First, the secrets of light. Second, bouncing back with light reflection. Third, real-world spherical mirrors. Fourth, the bending magic of refraction. And finally, shaping sight with lenses.
Okay, let's dive right into section 1, the secrets of light. Light is this absolutely fascinating dual-nature electromagnetic wave that can actually travel through the absolute emptiness of a vacuum. Now, I want you to just pause for a second and think about this number. 3 times 10 to the power of 8 meters per second. That is 300 million meters per second. This is the absolute maximum speed limit of the universe, the speed of light in a vacuum. It is so blisteringly fast that it could wrap around the Earth more than 7 times in a single second. Just mind-blowing. But despite that unbelievable speed, light is actually quite practical. Fermat's principle of least time states that in going from one place to another, light will always take the most efficient path. It ordinarily travels in perfectly straight lines. Honestly, it's almost like light is just trying to find the quickest, most direct shortcut home. But what happens when that straight line travel gets interrupted? Welcome to section 2, bouncing back, light reflection. The golden rule here is simple. The angle light hits a surface is exactly equal to the angle it bounces off. You've definitely seen this principle in action. Think about the word ambulance printed on the front of emergency vehicles. Why is it written completely backwards? Well, it's because of a property of plane mirrors called lateral inversion. When a driver looks in their flat rearview mirror, the mirror reverses that image laterally, meaning the left side becomes the right side. This allows the driver to instantly and correctly read the word ambulance and get out of the way.
Now, when light reflects, it creates an image, and it's absolutely crucial we distinguish between the two types of images formed. A real image is where light rays actually physically meet. Because they really meet, you can capture this image on a screen, like the movie you watch at the cinema. A virtual image, on the other hand, is an illusion. The light rays just appear to meet behind the mirror. You can't project it onto a screen. This is exactly what you see when you look at yourself in the bathroom mirror every morning.
Moving on to section 3, real-world spherical mirrors. This is what happens when we take that flat mirror and curve its reflecting surface inwards or outwards, quite literally like a soup bowl. There are 2 main flavors here. A concave mirror is curved inwards. Because of this shape, it is a converging mirror. It takes parallel rays of light and brings them all together to a single focal point. A convex mirror, though, is curved outwards. This shape makes it a diverging mirror, meaning it takes light and spreads it out wide.
And this brilliantly illustrates exactly how predictable this behavior is. When a ray of light passes through the principal focus, which we label F, it perfectly emerges parallel to the principal axis after reflecting. It's a really precise geometric dance.
Because a concave mirror can converge light to a powerful point or create magnified virtual images when you are really close to it, it's incredibly versatile. We use them in torches and car headlights to beam light straight ahead. Dentists use them to get an enlarged view of your teeth. We use them as shaving and makeup mirrors to see fine details. And on a massive scale, solar furnaces use giant concave mirrors to concentrate the sun's rays to generate unbelievable heat.
On the flip side, what about convex mirrors? Because they spread light out, they always provide an erect, meaning right side up, but diminished or smaller image. Why is that useful? Because by making everything look a little smaller, they squeeze a much wider field of view into the mirror. This is exactly why they are the absolute best choice for the side rearview mirrors on your car, or those big security mirrors you see at blind turns in traffic and in retail stores.
Section 4, the bending magic, refraction. This is where we finally solve our giant lemon mystery and figure out why swimming pools look way shallower than they actually are. This bending magic is called refraction. Simply put, it's a change in the path of light when it passes from one medium to another. But why does it bend? Because light actually changes speed depending on the optical density of what it's traveling through. Light travels faster in thinner, rarer mediums like air and slows down when it hits a denser medium like water or glass. To truly understand how much the medium matters, look at this number.
2.42. This is the absolute refractive index of a diamond, which is the highest of any natural material. What this number tells us is that light travels a staggering 2.42 times slower inside a diamond than it does in the vacuum of space. That dramatic slowdown and intense bending is exactly what gives diamonds their brilliant, fiery sparkle.
Let's break down the step-by-step physics of light passing through a simple rectangular glass slab. Step 1 is the entry refraction. As light enters the denser glass from the thinner air, it slows down and bends toward the perpendicular line we call the normal. Step 2, it travels in a straight line inside the slab. Step 3 is the exit refraction. As it leaves the glass and enters the air again, it speeds back up and bends away from the normal. When we map out those steps, the visual proof is striking. If you track the incoming ray and the exiting ray, something cool happens. Because the two faces of the glass slab are parallel, the bending in cancels out the bending out. The exiting ray ends up perfectly parallel to the original path. But, and here's the crucial part, it has been physically shifted sideways. This is called lateral displacement. The light stayed parallel, but took a little sidestep.
Which brings us to our final chapter, shaping sight with lenses. By understanding refraction, humans realized we could literally bend light to cure vision issues and magnify the microscopic world.
So the crucial point is how the shape of the lens dictates the bend. Just like mirrors, lenses come in different shapes. Consider the shape of a convex lens. It's thicker in the middle and thinner at the edges. When parallel light rays pass through it, the lens refracts them, bending them inwards so they converge at a single intense focal point. This converging power is exactly how magnifying glasses, microscopes, and your own eyeballs work to focus images.
Optometrists measure this ability using a metric called the power of a lens, which, simply put, is just the extent of convergence or divergence the lens achieves. It's measured in a unit called diopters. It is actually the inverse of the focal length. A converging convex lens has a positive power, which is why your glasses prescription might say +2. A diverging concave lens, used for nearsightedness, has a negative power. We've covered the speed of light, the bouncing of mirrors, and the bending of lenses. You now have the toolkit to decode the optics of your everyday life, so I want to leave you with a thought to apply right now. If a convex mirror always diminishes your image, and a concave mirror can turn you upside down, what exact kind of mirror is staring back at you when you look in your bathroom right now? Keep questioning, keep observing, and thank you so much for joining me on this explainer.